Hello everyone, welcome to Wallah. In this video, we are going to learn code optimization techniques. We are going to look at various techniques, how they help to optimize the code. So what is code optimization? The code optimization can be in terms of time or space. So you may save the time to execute the code, or you may save the space, or you may do both of the things like time and space you may save. So when I give you code, how you optimize equivalent code, that code should have the same logic, but either number of statements might decrease, that means number of instructions might decrease, or you may have the same number of instructions or more, but it may save the time. So that we have to look at how much space you take or how much time you take in equivalent code. If you can optimize or time or space or both, which is nothing but code optimization. Okay, here you have seen the all topics lexical analysis, syntax analysis, and SDTs, intermediate code. Now we are looking at code optimization, right? This code optimization you can apply in intermediate code, or you can after intermediate code generation, and you can also apply after assembly code generation, which is nothing but code generation. Okay, so there are two places where you can apply the code optimization, but in general the code optimization can be possible, right? If you want to do code optimization, that can be possible many levels. Like in compiler maybe two places, but in general you may apply at high level, that's fine, at high level code, or at high level you can say, or at intermediate level, that's after intermediate code, at intermediate code or at intermediate level, at low level, that is assembly level. Anyhow, in machine code we can't apply it, at assembly level you do it. Fine. So these are three places, but in compiler especially, you do these two things in compiler. This we do after intermediate code generation, right? After ICG, intermediate code generation. This one we do after code generation, after code generation, right? Once you generate assembly code, you can apply the code optimization at assembly level. But these two might have the similar techniques, but you have different programs, different code optimizers. One code optimizer works on intermediate level, other code optimizer works at assembly level. That it takes assembly level and gives assembly level. Here it takes intermediate code and produces assembly intermediate code. This one at high level, it's like editor side. When you are writing the code itself, the editor before compiling only, the editor might optimize that you can write your own editors to do that level, the things, right? Compiler will not worry about these things, but it's better to do some optimization at high level, so that much time can be saved to do these things. So at high level is basically what is this called as, you give C code and it also produces C code. That in editors you might be applying it rather than compilers. Before compilation, you can say that before compilation, if you want to work on this, you can try this while editing before compilation. Okay, but we will try to understand all the three simultaneously, how these are the things going to be applied. Now, as I told, the code optimizer, what it does basically, code optimizer, what it does, it optimizes the code optimizer or optimization. So if you write any algorithm, or you have the code optimization algorithm or program, it takes some code which might be machine dependent or independent. It try to produce optimized version, optimized code if possible. If not possible, it can't do anything, right? If possible. If not possible, it cannot, it will generate the same code. Now, what is this code optimization? Basically works on two levels, or it may worry about time, based on the time. So this code might take less time to run compared to this code or space, and this code might take less space compared to the given code, or it might work both run a time and save. This might save your time to run, or this might take less time to run, and this might take less space, right, compared to this one. This is about the code optimization. Code optimization can be applied to any program, which could be high level program or intermediate level program, or you have the assembly level program. When you are applying to the program, again, how do you apply the code optimization, locally or globally? So these code optimization techniques are various types again. So code optimization depends on statement. Sometimes within the statement you can apply, so that we may say statement level or instruction level. Like example, if you have a multiplication that you may replace with addition or some kind of shift operation, at single statement also you may apply the code optimization sometimes. And sometimes block level, a particular block, like if you are going to consider the control flow graph, we're going to work on basic blocks. So particular basic block, you have a few set of statements where the execution is sequential. You can apply at a block level, or you may apply various level. In the block may comes for depends on how you treat it. Is it loop or, but control flow graph is different, basic blocks are different. I'm talking about any kind of block that you write in the program. It could be function level. A function also can be considered as one block, or a for loop or if block likewise. And other one is if it is not a smaller block, especially you can say that procedural level, like block, special block is considered as procedural, right? Procedure level. You can say function or method. That's basically intra-procedural. We say that if you are applying to only one function, right, that's it's called as intra-procedural. Within the function. Another one is program level, which is basically considered as inter-procedural. Okay, there are various types of code optimizations. Like when you consider at program level, a single program you want to look at program level, you can apply the inter-procedural. These are various code optimization. Various code optimization techniques can be applied at different levels. As I told, that you can apply to only single statement, or you can apply to set of statements, or you can apply to whole function, you can apply to whole program, right? So these are very interesting code optimization techniques, but we are going to look at what are the techniques will be used in general, okay, locally or globally. So some are applied to locally or some are applied to globally. That means the what techniques are useful for us. Like we'll see some of the techniques, very interesting techniques we have. Code optimization techniques. What techniques they are? Code optimization techniques, CO techniques. Okay, a very simple technique that is called as constant folding. I'll list them. First one is constant folding. We'll see one or two examples. As you know, not many questions are there in the exam, but you should know the basic concepts. Like what is constant folding? Suppose you have a statement like x is equal to, I'm writing at high level. Understand? I'm writing at high level. Okay. Some statement you have at high level. And when you convert into assembly level, what you do is you have a lot of assignments, right? 3 and 4 you need to store somewhere and you need to multiply, right? In assembly level and intermediate level, you have to do a lot of things. But anyhow, this constant folding can be applied many places. Now, if you are going to do this, what is the equivalent code after applying constant folding? How many constants you can fold here? See here, 3 multiplication with 5. How much? 15 plus 2 is nothing but 17. This can be written as x is equal 17 plus a. This can be done with a single addition instruction at assembly level when you go to that place, right? But if you can optimize this in intermediate level, what happens is multiplication, addition, addition, 3 operations you have to do. Ignore the assignment. 3 operations. Now you are performing 1 operation. You can save the time, and also you can save the space. You need to store this these constants in some location, and you have to use them. Now you can directly write add instruction where the 17 along with some location data you can directly use within the instruction itself. So this is the advantage of constant folding. Likewise, you have a lot of techniques that you may apply at a high level or intermediate level or assembly level, right? In all the places you may apply, but this constant folding is not recommended to apply at assembly level. Why? In assembly level, you will never see the 2 constants in the same instruction, right? 2 constants, like I can't say add 2,3. One of them must be a register or memory location, right? So this is very important. You cannot perform this constant folding at assembly level, but you can use it in intermediate level as well as in high level. Second one, copy propagation. It is basically 2 types. You can propagate constant or you can propagate a variable. If you are propagating constant, how it looks like, 2 examples I am going to take. How to propagate the constant. Suppose you have x is equal 10 and y is equal to x plus a. Very simple example I am taking to help you to understand. Okay. Now what you do is, unnecessarily you are wasting the space x, and for this you need to move the 10 to the x, that you need to have the move instruction, and then you need to have one x location. Then what you do is, if really x has no other job, directly what you can do is, in place of x, this 10, you can move wherever you see the x, right? If x has no other job to do. Now x you can delete, simply this is sufficient. And what is the advantage of having y is equal to 10 plus a? You no need to take extra space for the x, and you don't need to execute 2 instructions. Now you can execute only 1 instruction, right? You don't need to execute the first statement especially, right? Second statement, like here you have a total 2 instructions, here you have 1 instruction. Here you have 3 addresses to deal y a x, here you are dealing with 2 addresses. So this is one advantage of propagating the constant. This is called as constant. X is equal to 10. 10 is the constant, right? This is the constant. The another one, variable also you can propagate. Sometimes the same code I am writing, let's say x is equal to some b and y is equal, let's say x plus a. What happens if x has no other job, only we are wasting the time to move b to x? That you can do replacing with b wherever you see the x. See, this b I can move to the x, that is, this is variable basically. You do not know the value at this point. The b can be given any value from the input side, or using scanf or any other functions, you can deal with this input. Now b plus a, again what is the advantage? The advantage is you have saved the 1 memory, and instead of executing 2 instructions, now we are executing 1 instruction. This is called as copy propagation. Either you can propagate the constant or you can propagate the variable, but here advantages, remember that in this copy propagation you need analysis where this x is used. If in between x is modified, you can't propagate this b, right? So you have to be careful. This b you are moving because x is not modified any time here, okay? Next, 3, you have a very simple technique called as a strength reduction. Strength reduction. Okay, what is the strength reduction? It's nothing but replacing the costlier instructions with the cheaper one. So you have some costlier instruction, right? You have some costlier instruction. or statement, what do? You replace with cheaper one. Cheaper one. What do you mean by costlier or and cheaper? The costlier instruction might take more time compared to cheaper one, or might take more space compared to the cheaper one. So let's look at, multiplication, right? Very simple example. Suppose you are doing multiplication, x is equal to a multiply with 8. They multiply with 8 is a multiplication here. Then you know that multiplication is costlier than addition and shift. So this might be replaced with a shift. How do you do this? It's, basically 8 means 2 power 3. When you are going at binary level, all the things should be converted to binary, right? So cheaper one is a very simple one. X is equal to a left shift with 3 bits. You will get the same answer. Which is less costlier? This one is a cheaper one, and this is a costlier one. If you know the multiplication algorithm in computer organization, you see a lot of registers to do the multiplication, because here there are so many bits. Let's say here n bits, nearly you need n registers to store the values. It takes much time. You need to add every register with other one. So this is a costlier compared to the shift. Now, not only this, you have other examples too. This is the first example, let's say. Second example, if you want to, let's say, a multiply with 2. This can be done two ways. One, you can take care of the take care with addition, or you may do, if you have the shift operator support, you can also do a left shift with 1 bit. Both will give you the same answer. Multiplication, division, this can be replaced with a left or right shift depending on how you use them. Okay, so this is one advantage of a strength reduction. But when you look at your all techniques, like you have the constant folding, copy propagation, a strength reduction, which order you need to apply? That's really a very difficult point. These algorithms may run repeatedly till it observed that there is no further optimization. Fourth one, some kind of simplifications, like algebraic simplifications. If you see at high level, I'm talking about high level, or even intermediate code, or even assembly code, sometimes you write x is equal to a minus a is really needed. It's nothing but x is equal to 0, right? This a minus a you can replace with a 0. You can use algebraic simplification to understand what a minus a does, right? X is equal to 0, you can use this. It's one optimization. Not only this, sometimes you write x is equal to a plus b minus a, let's say plus c. Then using your associative and commutative laws, you can bring this plus a minus a close. You can cancel them, right? You will get simply b plus c. And there are so many such optimizations you can do with the help of algebraic simplifications. Okay, maybe addition, subtractions, multiplication, divisions. You have identity laws, something like x is equal to a multiply with 1 plus b, something like you have. Then what you can do at high level, that a multiply with 1, you can simply write a. This addition can be saved, right? It's also kind of, I can say, it's kind of costlier and cheaper. The strength reduction also is a part of the algebraic simplification. Sometimes here you can see that it's a costlier, it's now cheaper, because a multiply with 1 you can replace with the cheaper one, that is a. Like similarly, while doing addition, you are doing something like a plus 0, that you can replace with a. So sometimes cancellations you apply, sometimes identity laws. You can use some algebraic laws within this programs, high level programs or intermediate level or assembly level, depends on what code you are dealing with. Very, very important, this is common sub-expressions elimination. Common sub-expressions elimination. You already used once, right? You can use directed acyclic graph, use DAG to eliminate common sub expressions. So this was the previous gate questions. DAG performs, or DAG is used for which of the following cases? Like it can eliminate common sub expressions. What do you mean by common sub expressions? Very simple. You have a plus b multiply with a plus b, let's say plus b, then okay, let's say x is equal to, here you see a plus b, how many times you have used? 2 times, right? No need to compute 2 times separately. You can compute once and then you can use it. So this can be done. Simply eliminate, like you can say that t is equal to a plus b, and you can optimize further if you want it later. T star t plus b. Okay, what is the advantage of this? Here you are doing 1, 2, 3, 4 operations. Here you are doing 1, 2, 3 operations only. Here 2 additions, 1 multiplication. Here 3 additions, 1 multiplication. Okay, so this is eliminating. How do you eliminate common sub expressions? But you know how to use DAG, right? The DAG we already used in intermediate code representations. For this, how do you use the DAG? First you do the addition. Okay, let's say left operand. Okay, either up or down arrows, but maintain only one side arrows. So a plus b, you have done this, and now you have the result of this too. Now what you do is you need to multiply. You need to multiply left same and right also same. That's a plus b. You need to take left as well as right. After this, you need to perform the addition. So this whole thing will be the left side, and b, this b only the right side. So this is DAG. Now using this DAG, you can see that for this a plus b, you just need one calculation. You don't need to do twice computation, right? Which is really interesting, and we have done some practice on common sub expression elimination in intermediate code representation only. So there I use the DAG to find the minimum number of nodes and edges. The 6th one. What we have seen so far, we have seen the constant folding and copy propagation, in which constant propagation and variable propagation. We have seen strength reduction, and we have also seen the eliminating common sub expressions, and likewise you have algebraic simplification, and so many are there. And now we are going to look at the very interesting optimization is like loop optimizations. Loop optimization. There are various loop optimizations in which you can move the code before or after the loop to save the time, or sometimes you can merge the 2 loops, loop merging or loop combining or loop fusion. There are many names here. Third, you can also do loop unrolling. You can also eliminate the induction variables. If you have many variables which depends on the loop, you can use less number of variables by eliminating some of the variables. Induction variables elimination. Okay, at loop level we are applying here. So within the loops you can also apply various optimization techniques. Okay, let's look at what is code motion. Okay, the code motion is actually we are doing within the loop. Okay, code motion. What is the code motion here? See here, I have some statement like I is equal to 0, I less than n, I increment. Some code is there, don't worry about it. So somebody is trying to assign x is equal to 10 here, and later they are trying to write y is equal to a multiply with, let's say, x. See here, or let's say I multiply with x, because we need I, right? Let me use that. And you might be using y for some purpose here. Let's say I want to print y, or you want to do something else with this. Okay, let's say you are doing printing y. Okay, I'm just writing in some simple form. Okay, I'm not writing that, just assume it. Maybe you want y value after this, so that's why you are doing it. Y is equal to y plus something like that. Okay, some updates you are doing it, but not exactly this way we write. we just change the statement as per your requirement, right? Let me write better way. Y is equal to y multiply with x. You keep on doing something repeatedly. Okay, how many times that repeated multiplication you do it with a 10. Okay, y initially has some value, don't worry about it. Now what is the problem with this? Every time you have x is 10 only. Why are you doing this many times, n times? Why do you want to assign the 10 to x? Not required, right? This you can move before this code, so that you can save the, instead of executing this n times, now you will execute only one time. So how many instructions you have saved? N minus 1 times, no need to execute this one if you keep outside. Like x is equal to 10, we keep outside, and high level I'm explaining, but this can be done at assembly level as well as at intermediate code. But that code looks lengthy, that's why I'm not writing it. Now simply you can write y is equal to y multiply with x. Right? How many instructions we have saved? N minus 1 times. Previously this was executing n times, now executing 1 time. That is, overall you have saved n minus 1 times to execute. But each time you execute, other 2 instructions also need to be executed. But anyhow, that we can't reduce as this statement is there already. Fine. This is called as code motion. You can move this code above, sometimes possibly below. If it is you can also write this after, then you can move, like you have, let's say _z is equal to 100 is there, and you might be using _z later, so _z is equal to 100, no need, right? You can move after also if you want it. So this is called as code motion. You can save the number of times that statement within the loop is executing. You can move outside the code, you can execute less number of times. Now loop combining or loop merging. Why do you want to merge the 2 loops, or why do you want to combine? Because see this code, for I is equal, let's say 0, I less than n, I increment. You are doing, let's say, the previous kind of x is equal to x plus 10 you are doing. Okay. And another one, for j is equal to 0 and j less than n, or I less than n, you can say that j increment, you are doing something like y is equal to y multiply with, let's say, 2. Now don't worry about other optimizations, like here you can do strength reduction, that things you can take care additionally. Now can I combine these 2 loops? Is that possible or not? See here 0 to n, 0 to n minus 1, 0 to n minus 1. Here x is repeatedly adding with 10, here y is repeatedly multiplying with 2. Right? You can do simultaneously, right, within the single for loop, like for I is equal to 0, I less than n, I increment. Okay. Now I don't need a j, I don't need a j here. I can do computation just with x, just with I. X is equal to x plus 10. Along with this, you can copy this. Y is equal to y multiply with 2. Now, is it doing the same logic of this program and this program? Will it be same? Yes, because the x value, whatever you see at the end of this loop, will be the same after this loop also. And what is the y value after this for loop? It is also same here. Only the thing is, here x is computed n times, x is updated n times, here y is updated n times independently, but now every iteration both x and y are updated. So this is optimized version, and this is executing more number of times, so it takes more time compared to this one. You can check how many instructions are executed, here how many instructions are executed. You can try that as an homework. Okay. Loop merging. Now we'll look at a loop unrolling. Loop unrolling. What is this loop unrolling? Again, very simple program. You can see here I, suppose you have I less than, let's say, 100. Of course, you can also write some variable n, but I'm just writing it. I plus plus. You are doing something like maybe printf, to understand simply. Printf, you are writing, let's say, a. Now what is the job of this for loop? Printing this a 100 times, right? 0 to 99 times. Now the same job, what's happening here, to print this a 100 times, what you are doing is every time these two instructions are executed, right? First this one, then after printing this, you need to execute this one and this one to print this one. That is, every print you are additionally two instructions you are executing. Means for 100 A's, you are executing other two instructions every time. That means nearly 300 instructions you are executing overall to print just 100 A's. How 300? First time 1 2 3, first A. Second A, 1 2 3. So 1 2 3, 1 2 3. See, every time three instructions. The 100 A's total 300 instructions. At the end, this two will execute, this will fail, right? At the end. So 302 instructions you are executing. How many total? You can see that 302 instructions. How do you get it? Each time three instructions. Every A you print, there are three instructions you are executing. So 3 into 100. At the last, you execute this two and you will fail. You will not go inside. So 300 plus 2. Plus 2 for failing the condition, and every time you execute, for every true condition, you will execute 3. So 302 total instructions you will execute here. Are statements. Just say statements. Now, can you have the better optimized version of this code? Yes. How do you do that? Called as unrolling. So this 100, you can make it off. What happens if you make it off? For I is equal to 0, I less than 50. Of course, you can make it off further, but one time unrolling will make 50, two times unrolling will make 25. But first time when you unroll it, what happens? This code is going to be copied twice, that is duplicated twice. You will get printf a and again printf a. So two times you will copy the body of the for loop. Now look at how many instructions total overall will be executed. Every time 4 instructions, total 50 times you will print 2 A's. Means total 100 A's only, but each time 2 A's, total 50 times will print. So what happens is that 50 times A will print A, the 2 A's will print 50 times, but each time total 4 instructions. First time 1 2 3 4, next time 1 2 3 4. To each time 4 instructions. To print 50 times double A, the 4 total instructions will be executed, plus 2 to fail the condition. Increment and fail goes outside. So 50 times 4, 200 plus 2, 202 instructions now. 202 instructions executed. Here 302, which is the better one? This is the better one. If we do one more time unrolling, this 50 become 25 and this 2 printfs will become 4 printfs. That is 4 A's will print 25 times, 100 only. 2 A's you are printing 50 times, 100 only. 1 A you are printing 100 times. Logic is same, but the loop unrolling, the concept is that copying this block, this body twice and doing this condition into off, that makes sense, like you are unrolling this loop. So this is also kind of optimization. Okay, you have other technique. Let me discuss first the induction variable. If you really want it, just induction variables. Simple example I'll give. It is also loop optimization, induction variables elimination. Those variables which depends on the loop, we call them as induction variable. Okay, example, see, for I is equal to 0, let's say j is equal to 0 and I less than 100 and I increment, z decrement, and you are starting, let's say k is equal to 0 and you want to do something like x is equal to I multiply with j plus y. Okay, a is equal to x multiply with, let's say, x adding with k, and you're doing k plus plus, something like this. You're writing this code. See how many induction variables are there here? So many, right? So many induction variables. Which variables are changing frequently. Here you can see what variables are changing. I changing, j changing, k changing, x changing because it depending on ij. Y is not changing. So y is not changing, it's not induction variable. And k is changing, I told that, right? X changing, and a, every time you are updating the value of a, that means a also somehow it's changing. But among them, which variables you can eliminate? Not every variable, right? So instead of I, j, k, can I use only one variable among these three? Remaining anyhow, you know, this a is equal x plus k, that you can do at the end, but be careful whether it is right or wrong. Okay, so you can do at the end, but k value you should treat carefully. Okay, now I'll keep everything, only I worry about I, j, k. Instead of this many statements, can I do the better version of this code? See, I'll just write for I is equal 0, I less than 100. Okay, every time the value gets 0, that's different. I increment. Now what I do is x is equal to I multiply with I plus y is not changing anywhere, it's just constant, assuming in this loop. A is equal to x. In place of k, can I use I or j? Yes. So I'm using only I. Now k plus plus not required, I'm already incrementing it. See, I and j I can eliminate. J and k I can eliminate. J and k are also induction variables and they can be eliminated here. Why? Because I already doing the similar job, so you can take care with the I. Whatever I is doing at any time, while adding it, see, k is same as I and j, and here I and j and k same. So you can use ij, you can use one variable instead of I, j, k, three variables. So I've used I to do the same job, This is called as eliminating induction variables. Okay. Now we have, a very important concept like the basic blocks. Before discussing this question, this basic blocks used in control flow graph. So let me explain control flow graph before coming to this. What is this control flow graph? The whole program is divided into controls and edges, basic blocks and edges. Control flow graph. It is basically a collection of nodes and edges, collection of basic blocks, basic blocks, and also edges here called as control or control edges. So every program that you write will be converted into control flow graph to optimize. So what is this control flow graph? Let me write simple code in 3 address form, so that easily I can make a control flow graph. Suppose I have x is equal to 10, y is equal to a multiply with x. If y greater than 100, I do something here. Let's say z is equal to z plus y. Else I do, let's say z is equal to z minus y. And maybe you are printing z, let's say. How to draw print? It's just 3 address code, right? Just 3 address code. This code, how do we convert into a control flow graph? What is this basic block first? What is this basic block? Controls anyhow we will get easily once you know the basic block. Basic block is nothing but a set of instructions which are executed sequentially, and the control only enters at the begin and leaves at the end. So you need to collect as many as instructions possible, maximum set, but that sequence is the execution, execution sequence is going to be sequentially executed. Okay, if you try to understand the code, first to make a basic block, you need to understand how the control flow happens. See, x is equal to 10. The first, then next y is equal to, after this you will enter this one. From here the control either goes here or goes here. That means this instruction cannot be combined with this. If you combine it, these are not sequential. After this you may go here or you may come here. Are you getting my point? But after this always comes here, after this always comes here. because nobody coming in between. The control only lives at the end and enters here. So these three statements I can keep in the same block. X is equal to 10, y is equal to a multiply with x, and if y less than 100. You're not drawing flow chart for algorithm. Remember that flow chart is different. This is a control flow graph. All these three statements you can keep together in a sequence because control only enters here and only lives here. Remember that. Nobody should enter in the middle, and nobody should, means no basic block should not leave the control from the middle of the block. That means the control only enters here, execution sequence I'm talking about, and after executing this three, control should leave here. But after this, the control may not be sequence, it might go here or there, doesn't matter, right? So but these three instructions, control only goes in a sequence. Fine. Now after this, it might go here or it might go here. Clear this point? And after executing this, definitely will come here and also will come here. Now I can't combine the z is equal to z plus y here because this should be separate basic block. Okay. And z is equal to z minus y, you can't combine with anybody, it's separate. Now the question is, can I keep this print z with any of this? No. This print z may execute it after this or after this. So for both of them it should be available. So we can keep print z. Now from here the control may enter here. No need to say true or false. Remember that. Here we are not drawing the flow chart. We are only drawing the control flow graph. That's it. One might be true, other is false. That's it. Okay. After this, control enters here. After this, control enters here. Now you look at, there is no basic block. The control will come in the middle and will live in the middle somewhere, right? Control only enters. So remember how the basic block is. If it is a basic block, control only enters here and only lives here. But the controls may live many at the end, but nowhere the control is living in the middle, right? Nowhere in the basic block. So after only it should. Why these controls are basically there? They can be made it as conditional or unconditional jumps. They are actually jumps only. If you look at the assembly code, jump to this address or jump to this address. Maybe conditional on this one, but they are actually jump instruction. What is the advantage of making this code? Because this basic block you can move anywhere in the program while optimizing, and you can load this basic block. You can optimize here only. No need to load whole program. So when you apply the optimization at basic block level, it is so easy because few instructions are there and you can optimize easily. Okay, that's one advantage. Flexibility is there in moving the code also. Now, how many basic blocks we have? In the exam they may ask, how many basic blocks? 4 basic blocks. 4 basic blocks. How many controls we have? You can see how many controls we have. 1, 2, 3, 4. 4 controls. Sometimes they may ask number of nodes and edges. When they ask nodes, then just keep one thing here. Start a node and you will connect, and there will be end node. Stop, and you will connect like this. So now number of nodes when they ask 1, 2, 3, 4, 5, 6. You will say 6 nodes. Here the start and end we do not consider as a basic block, but they are nodes including basic blocks. Basic block also nodes. Here you can say every basic block is a node, but node need not be a basic block. So when they ask number of nodes, include the start and end. If they say exclude it, you should remove it. Okay, number of edges, how many? 1, 2, 3, 4, 5, 6 edges. Here we have only 4 controls, but these are the edges. These two we don't call as what? Control, because obviously that should enter here and obviously should go to the end. So they are actually called as edges. We don't call them as controls, but remaining these 4 you can call as edges or controls. Fine. This is about control flow graph. Now we have this kind of GenSet, KillSet. These definitions are used in we have some kind of analysis, like what we say live variable analysis. If you really want to compute live variable sets, then at basic block level you are going to do this kind of computation. Okay, GenSet and KillSet. So you need to learn this two kinds of things, like when you do live variable analysis. Or liveness analysis, you are going to look at in this chapter especially. If you want to compute live variables at particular basic block or at particular statement, you should know how do we compute this. It is called as backward analysis, because you can't compute from top to down. You need to compute this analysis from bottom to top. It is a backward analysis. It's very easy to compute live variables if you do backward analysis. If you do available expression analysis, there are various kinds of optimizations. Available expressions analysis. If you want to do this kind of analysis, you have to do forward analysis. Top to bottom we are going to do forward analysis. And there are many other analysis, like you wanted to find use def change, then you can use forward analysis, again similar to this. You want to find the definitions of the variables, then you can do forward analysis. And this is the most important technique for you, and they may ask very simple. Here you are going to use the concepts like finding GenSet, finding 𝐂𝐤𝐴, finding live variables at particular statement or at particular basic block. These are the three important topics in the live variable analysis you're going to compute. So here there are some questions for you. You need to learn these things: GenSet finding, 𝐂𝐤𝐴 finding, and live variable analysis. So I'm leaving to you, and definitely I'll come up with practice session. There I'll be discussing. Please try to do this kind of analysis. Try to learn what is the GenSet for this basic block. For this basic block, you can compute GenSet. Okay, you can compute GenSet. You will get some set of variables you will have here. What are the variables are generated here? What are the variables are present in the GenSet? So here it's just like similar to the live variable definition. And if you look at something here, right, let's say I'm using B, but in future, see here, when I'm using B, in future, is anybody using it? Anybody using it? See that from B you have above definition, right? Let's say this point, I have the B definition, I'm using it. Anybody modifying it? No, right? So B will present in the GenSet. C I have already, and I am using, in between nobody writing, so C also there in the GenSet. And but A you can't, because nobody reading A, so A you can't. A you can't. A is not present in the GenSet. What about C? C already covered, right? C. D, you are having definition already, you are reading it, in between nobody writing, nobody changing the definition, so D is also there in the GenSet. It's just like a live variable, but live variable look at whole program. This GenSet will look at only in this basic block. We don't look at other block at all. Live variable depend on whole future program point, and this one is only depends on here. What about B? B we might have a definition, but in between we are not reading at all. So B, C, D is actually set of variables we need alive here. We need alive here. So B, C, D, you need present. For this set, for this basic block, the GenSet is B, C, D, because they should present before executing these statements. If anybody deleting any of these three variables, they lose the definitions. I don't need A because I'm defining inside. I don't need B because I'm defining inside. But B, C, D, if you don't have these three definitions, you can't execute the statements. The GenSet will give you what are the variables need to be generated before this block. You may assume that. 𝐂𝐤𝐴, what are the variables will be killed or will be defined newly in this set? You can see left side, A is defined. So A, previous definition was killed, a new definition is given. So A is killed and B is killed. Very simple to look at it. So that's why we have GenSet and 𝐂𝐤𝐴. GenSet is a B, C, D. We don't say all these variables are a GenSet, okay? Only B, C, D. 𝐂𝐤𝐴 I have given. If I ask next question is 𝐂𝐤𝐴 A comma V, just answer it. Here A comma V, this one. Very simple. Those variables you are defining in this block, means you are assigning with a new values. They are called as kill variables, or the variables within the kill set. Okay, similarly you may try various other questions, like this. It is also similar. Live variable set at S1. Now the question is about only this one, right? At this point, what other variables are live at this point? Now for that you need to look at whole program. That's why this analysis depends on the backward. If you start computing from backward, this can be easily computed. But anyhow, only two statements are there, you can check it. When somebody asks at S1, just look at before this year. At S1 means just before S1, remember that way. Now what are the variables are live at S1? Before executing just S1, what are the variables should be live? So now look at same like GenSet definition. What variable we are reading? A we are reading. That means before you are defined, now you are reading. In between this, you don't have any change. Right? This is different. When you have A is equal B plus A, which one is executed first? This one is executed. Of course, this one is executed maybe, but assignment happens like this. So this, after executing this, the definition of A will change. So A will be changed after executing B plus A. Remember that. So for this execution, before this, no A is modified. That means A need to be alive. No A need to be live. Because of that, A need to be used in this statement. So here A is live. What about B? B is also live because this statement is using B, and in between you are not writing. C is live because in between you are not writing a C. You are not changing the value of C. D also live. A, B, C, D. A, B, C, D are live, just like GenSet, but that was one basic block. And this you might look into whole program. I'm not saying basic block, but I'm just talking about at S1, what other variables are live? A, B, C, D. Then why not V? If you say V is live, then somebody has to read in the future. Here, if you say V is live, and is anybody reading V? No. Right? That's why V is not live. V is not live. Okay. That's why we have the answer A, B, C, D. We have the answer A, B, C, D. Now, what are the live variables at S1? Is it same code? Just wait. Now we'll do at S2. At S2. Okay, small change in the code at S2. Can you do this? At S2 means you only look at this point. You only look at this point, but whole future program you should look at. Now there is no use of this S1 because we never go back. It's not a loop to repeat, right? So what you do here is you need to find C is used, so C is live. D is read, so D is live. And V is not live because V we are not reading. So only C, D are live. That's it. Very simple. It has some definition and somebody reading it, and before reading, any read is fine, but before reading there is no definition or no assignment to that variable. Nobody changing the meaning of that variable. Okay, so at least you are reading C. In between these two program points, at this point and at this point, nobody is intervening the value of C. Nobody changing the variable C. That's why we say C and D are live because we need them for the future. We need them for the future. C and D already have a definition here, and that same definition we are going to use them because they are live at this point, at this point. Okay, so I have tried to explain some of the important techniques, but you need to practice how this analysis we do, and take the whole control flow graph and try to find out at every statement what are the live variables. Then you will understand better way. So we have seen many optimization techniques, right? What are the optimization techniques we have studied? Here we have studied optimization techniques such as like constant propagation, constant folding we have studied first, right? Then we have studied constant propagation and variable propagation. So I call it as the copy propagation. Fine. Then we studied like strength reduction, if you have recalled all these points. Common sub-expression elimination using DAG. and then some algebraic simplifications. There are many other code optimizations. I've just discussed very important ones for the exam. Loop optimizations. We have studied various kinds of optimizations at loop level. Okay. And also some techniques used in live variable analysis, like how to find the GenSet and 𝐂𝐤𝐴. To find the live variables for 2 statements only have helped, but you should practice for the whole program. Okay. Yeah. Thank you so much. I know this code optimizations will help you to understand how to apply this few important optimizations at in a given program, and sometimes you will be asked with the program and find out what optimizations can be possible on this given code. So you can just look at what are the techniques you have learned and try to apply them. Thank you so much, and I hope you have enjoyed all compiler session. See you soon with the many practice sessions.